So how do you do a problem that involves Newton's second law and acceleration? This is a very typical type of problem where you have, in this case, a 5 kilogram wagon that's pushed with a force of 20 newtons to the right. And what is its acceleration if there is no friction? And then what is the acceleration if there is friction? Now, these steps that we used before are going to be 100% still valid. These are still the steps that we're going to use. Except in this place where you sum the forces in the x and y direction, you will either, if it's in equilibrium, set equal to 0, or if it's not in equilibrium, if the sum of the forces does not equal 0, then the sum of the forces, you'll use second law, is the mass times the acceleration. Okay, so let's go into that. We have a picture, then we want to draw a free body diagram. So here's the dot for my wagon. The forces acting on the wagon are gravity, always gravity pointing straight down. Labeled Fg, and the normal force, Fn, and here we go. I'm just going to call this Fa, the applied force. Okay, now in this question, the wagon is going to accelerate in the x direction. I'm going to call that positive x direction. And so we don't really care about summing the forces in the y direction because the sum of the force in the y direction is going to be 0 because these forces are balanced. So all we're going to do then is we're going to sum our forces in the x direction, and the only force in the x direction is the applied force. And so that is not 0. You can tell it's not 0. That's going to be the mass times the acceleration is going to be our applied force. And then at this point we can plug in some numbers. And so we know that the mass of our object is 5 kilograms. We're looking for acceleration. It's pushed with a force of 20 newtons, so that is going to be my applied force. I'll divide both sides by 5. You could have solved for A first. That's usually what I do, but I know that a lot of people are uncomfortable with that. 5 kilograms to give me an acceleration of 20 divided by 5, 4, remember, meters per second squared. That's our unit for acceleration. Okay, so what happens if there's a frictional force? Well, things will change just a little bit. I'll redraw my free body diagram. Remember, this is the force of gravity. It goes straight down. It never is at an angle, always straight down. Remember also that the force of gravity equals the weight, which is the mass of an object, times the gravitational field strength, or 10 meters per second squared. Here's our normal force. These should be the same length. Our applied force. And now there is a frictional force. And so if the wagon is moving this way, the force of friction will act backwards. So here's our force of friction. And then same deal. If I wanted to sum the forces in the y direction, the sum of the forces in the y direction are 0, so you don't really need to do that. We're just going to sum our forces in the x direction this time. And that gives us the applied force that's positive, minus the force of friction that's negative. And that is not equal to 0. Again, this is going to be Newton's second law because this object is accelerating. So that will be equal to mass times acceleration, or the applied force minus the force of friction, which in this case is 20 newtons divided by 6 newtons. Mass again is 5 kilograms. Acceleration, and so 20 minus 6, that gives us 14 newtons divided by 5 kilograms, and that's something like 2.7, or maybe, I'm not sure. All right, so that is how you do these problems, and remember that's meters per second squared. Oops, meters per second squared unit. Okay. Things don't change if this wagon were to be pulled at an angle, right? Instead of being pulled straight, if I pull this wagon at an angle, the force of the applied is changed. And so that would change my free body diagram. That would change my force diagram so that I would have gravity, right? The normal force, and then we would have this applied force, and maybe I need to make my force of gravity a lot bigger here. And then depending on whether you have friction or not, that will go in this direction. And so just like we summed the forces on an object that was sitting still being pulled at an angle, we will do the same thing for an object that is accelerating and being pulled at an angle. That same thing being, we'll use the force components to find the applied force in the x direction and the applied force in the y direction. And that's basically all Newton's second law. All of this stuff that we're studying right now is called dynamics, because things are moving rather than statics when things are stationary.